Right now, in a control room in Pasadena, California, a small group of engineers is watching a single green line on a screen, and every one of them already knows it is about to go flat. They are not afraid. They built this exact moment on purpose, years in advance, and now all they can do is wait for it to arrive. Somewhere behind that line, roughly 900 million miles away, a machine about the size of a school bus is falling toward a planet made of gas, firing its thrusters harder than engineers ever designed them to fire, just to keep one thin radio signal pointed at the only people who will ever hear it. It is not a malfunction. It is not an accident. It is an execution ordered months earlier by the very people now watching it happen, and in a few minutes, they are going to watch it succeed. This is the story of Cassini, and it moves past the discoveries you may have already heard about at Saturn, the rings, the moons, the storms, straight into what its own team chose to do to the spacecraft itself, on purpose, near the very end, and why that choice was almost certainly the right one. This channel tries to explain real space missions without reaching for exaggeration, and this is a case where the ending is not a footnote. The ending is the entire point. Both halves of that spacecraft were named after men who had done similar work centuries earlier, with nothing but glass and patience. Giovanni Domenico Cassini, an Italian astronomer who spent decades at the Paris Observatory, found the gap in Saturn's rings that still carries his name, and discovered 4 of its moons using nothing more than a good telescope and years of careful watching, back in the 1670s. Christian Huygens, a Dutch astronomer working a generation before him, was the first person to work out that Saturn was surrounded by an actual ring rather than a blur, and the first to spot Titan at all. 3 centuries later, NASA and the European Space Agency put those 2 names on a spacecraft and a probe built to finish the work those men could only guess at from a rooftop in Europe. Cassini left Earth on October the 15th, 1997, riding a Titan 4B rocket out of Cape Canaveral, carrying a European lander called Huygens tucked against its side. Before it even reached the launch pad, protest groups had spent months trying to stop it, in court and in the streets, because Cassini carried 3 separate generators fueled by plutonium, together holding about 33 kilograms of it, roughly the weight of the heaviest suitcase an airline will let you check without charging extra. Cassini needed that plutonium because sunlight at Saturn is only about 1% as strong as it is here at Earth, far too weak for the solar panels that many newer spacecraft rely on instead. If you had watched that launch from the causeway at Cape Canaveral, you would have seen some of those protesters standing with signs about exactly that. The protesters were worried about a worst-case explosion scattering that material into the atmosphere. NASA argued that containment would hold even through a launch failure. The rocket flew, the containment held, and the argument went quiet for 2 decades. It would come back in a very different form at the other end of the mission. The same underlying debate over flying plutonium at all resurfaces almost every time NASA needs one for a new mission, and it has never fully gone away. It took nearly 7 years to reach Saturn, swinging past Venus twice, then Earth, then Jupiter, stealing a little speed from each planet's gravity on the way past. On the way by Jupiter in the closing days of 2000, Cassini's cameras produced the most detailed full-color portrait of that planet, taken up to that point, a kind of warm-up exercise for instruments that would spend the next 13 years staring at Saturn instead. On July the 1st, 2004, Cassini fired its main engine for more than an hour and a half, slowing itself down just enough for Saturn to catch it. It became the first spacecraft ever to orbit the planet. If you had been standing in that control room, you would have been watching a machine that had already survived 7 years alone in the dark, arriving somewhere none of the people who built it would ever see with their own eyes. Saturn itself is large enough to hold more than 700 Earths inside it, and Cassini would spend the next 13 years learning what that much planet actually does. 6 months later, on January the 14th, 2005, Cassini released the Huygens probe toward Titan, Saturn's largest moon, a world wrapped in an orange haze thick enough to hide its own surface from cameras. Huygens fell through that haze for more than 2 hours, and when it landed, softly, on a cold plain scattered with rounded ice pebbles, it became the first human-built object ever to land in the outer solar system. If you could have stood on that plane yourself, the sky above you would have been a deep orange haze, lit by a sun you could not have picked out directly. Huygens kept transmitting from the surface for about 90 minutes, far longer than its designers had dared to promise for a probe built to survive a landing at all. Then Cassini's own orbit carried it below Titan's horizon, breaking the radio relay between them, and Titan went quiet again. For years after that, Cassini did what long missions are supposed to do, except it kept finding things nobody had scheduled it to find. At Saturn's North Pole, it photographed a 6-sided jet stream wrapping all the way around the planet, a genuine hexagon, each of its sides longer than the diameter of Earth, holding its shape and spinning in place instead of drifting apart the way every other cloud band on the planet does. Nobody had written an explanation for that into the mission plan, and more than a decade later, scientists are still arguing over the mechanics of it. In December of 2010, an amateur astronomer spotted something new erupting in Saturn's northern hemisphere, and Cassini turned its instruments to watch it grow. Within days, the storm's head had swollen past 10,000 kilometers across, generating lightning at a rate of roughly 10 strikes a second, faster than anything measured on Saturn before. Over the following months, it stretched out and wrapped itself most of the way around the entire planet, one continuous storm system circling a world about 9 times wider than Earth. Cassini was already there, in orbit. Instruments pointed the right way for the whole event. No telescope on the ground could have followed it that closely for that long. Cassini also studied Saturn's moons one at a time, and one of the strangest got a single close pass in September of 2007. Iapetus turned out to have one hemisphere as dark as fresh asphalt and one hemisphere almost as bright as fresh snow, split cleanly enough that observers a century earlier had assumed they were looking at 2 different objects. Running along its equator, Cassini's cameras found a ridge more than 1,000 kilometers long and in places taller than anything on Earth, giving the small moon an odd walnut-shaped profile that nobody has fully explained since. Another of Saturn's small moons, Mimas, carries a crater named Herschel that stretches nearly 140 kilometers across, close to a third of the moon's own diameter. Photographed clearly for the first time by Voyager, and then in much sharper detail by Cassini, Mimas turned out to bear an uncanny resemblance to a fictional superweapon from a 1977 film purely by coincidence, since nobody had photographed that crater clearly enough to notice the resemblance until decades after the movie came out. And on Titan, Cassini's radar spent years mapping through the haze that ordinary cameras could never see past, finding lakes and seas of liquid methane and ethane spread across the moon's polar regions, the largest of them named Kraken Mare, big enough to earn the word sea rather than lake. Titan turned out to be running its own weather cycle, methane evaporating, forming clouds and raining back down, doing on that frozen moon roughly what water does here, just at a temperature cold enough to freeze carbon dioxide solid. None of that storms or hexagons or methane seas is why this mission is remembered today. What people actually remember, and what ultimately decided this spacecraft's fate, happened on a small, icy, unremarkable-looking moon called Enceladus. Cassini flew that entire mission, storms and hexagons and methane seas included, on computer hardware finalized in the early 1990s, years before most home computers came with a mouse as standard equipment, and long before anyone on the team could have imagined carrying more computing power than that in a pocket. That is not a knock on the engineering. It is closer to the opposite. Nothing about Cassini's 20-year run happened because the machine got lucky. It happened because the people who built it, and the people who kept flying it decades later, refused to let something built that carefully fail on their watch. For 13 years at Saturn, aside from Huygens and a handful of moon flybys close enough to feel almost like company, Cassini worked entirely alone, sending its findings home in a whisper of a signal that arrived by the end of the mission, well over an hour after it was sent. No other machine, and certainly no person, was ever coming out to visit it. In November of 2005, images came back from Cassini's cameras, captured by the mission's imaging team under planetary scientist Carolyn Porco, showing something nobody expected from a moon barely wider than the state of Arizona. Thin jets of ice and vapor were shooting out from cracks near its south pole, later nicknamed the Tiger Stripes and formally named, like most features on this small moon, after places from the tales of 1001 Nights, tall enough to be seen from space and feeding material into one of Saturn's outer rings. Here's the detail that would end up mattering more than almost anything else this spacecraft ever found. Enceladus was not a dead ball of ice. Something underneath it was active. Over the following decade, Cassini kept going back. Gravity measurements taken during close flybys in 2010 suggested there was liquid water moving beneath that icy crust, and later analysis of the moon's very slight wobble all but confirmed a global ocean sealed under miles of ice and permanent darkness. Then, on October the 28th, 2015, Cassini flew directly through one of those plumes at an altitude of only 49 kilometers, a little farther than a marathon route. Its instruments caught something scientists had been hoping for and half expecting not to find: molecular hydrogen. A team, led by scientist Hunter Waite of the Southwest Research Institute, spent months confirming what that hydrogen meant, and published the result in the journal Science in April of 2017. Hydrogen escaping from Enceladus' seafloor is the kind of chemistry you would expect from hydrothermal vents, the same kind of vents that support entire ecosystems in the deepest, sunless parts of Earth's own oceans. It does not prove there is life in that ocean. It means that ocean has fuel life would need, if anything is down there at all, The following year, in 2018, a separate analysis of that same plume data, led by physicist Frank Postberg, turned up something else. Buried in the ice grains Cassini had flown through were complex organic molecules, some built from at least 15 carbon atoms, heavier and more structurally complicated than anything a simple chemical reaction usually throws off on its own. Here's the part that is easy to oversell. Nobody is calling that biology. It is, at most, raw material biology could work with, sitting in an ocean that already had the energy to put it to use. Say plainly what Cassini did and did not prove, because the difference matters. Enceladus has not been confirmed to host life. Nobody has found a single microbe there, then or since. What Cassini confirmed is narrower and still remarkable. An ocean, liquid, in contact with rock, warmed enough to stay that way, mixing with chemical fuel life elsewhere in the universe is known to use. Conditions, not confirmation. That distinction mattered enormously to the people making the decision you are about to hear about, and it is the distinction worth holding on to for the rest of this video. And that finding is the one that condemned Cassini. Not because anything went wrong with the spacecraft, because something had gone right on Enceladus. Cassini was never built to touch a place that might support life. It left Earth clean by the standards of 1997, which was nowhere near clean enough for a habitable ocean world. Somewhere in its structure, almost certainly, were microbes that had hitched a ride from Earth and survived years of cold vacuum. Space agencies operate under a shared, informal agreement not to contaminate other worlds with Earth life, particularly worlds that might already support their own. There is no courtroom attached to it, and no binding statute behind it. Think of it instead as a professional code, honored by the world's space agencies, because the science itself depends on it. If a future mission ever finds something alive on Enceladus, or on Mars, or in Europa's ocean, and it later turns out the sample was contaminated by hardware that flew out from Earth without proper precautions, the discovery becomes worthless. Nobody would ever be able to prove the life they found was not simply ours to begin with. By the middle of the 2010s, Cassini had also burned through nearly all the propellant it carried to Saturn, and every course correction from that point forward had to be treated as one of the last. Mission planners weighed a small number of ways to end it safely. Leave the spacecraft in orbit and hope nobody ever lost control of it for decades or longer. Even a stable-looking orbit drifts over time, and with no fuel left to correct it, nobody could guarantee where an uncontrolled Cassini would eventually end up, decades or centuries from now. Aim it away from Saturn entirely, at enormous cost in fuel it no longer had. Or fly it deliberately into Saturn itself at a time and place the team could choose, so that if Cassini carried anything from Earth, it would end its life as vapor in a gas giant's atmosphere rather than as a crash landing on the one moon in the solar system, where that would matter most. They chose the third option. Given what Cassini itself had just found, it is hard to argue they chose wrong. There is a real irony sitting inside that decision, worth pausing on for a moment. The very same instruments that flew through Enceladus's plume and found the ingredients life would need were, in that same instant, also the greatest contamination risk this spacecraft carried. Discovery and risk traveled on the same machine at the same time, and only one of them was allowed to keep happening. NASA had actually been planning this ending for years. Cassini's second mission extension, called the Solstice mission, was approved back in 2010, built from the start around the knowledge that the spacecraft's own fuel supply would eventually force a decision, and around the fact that Enceladus, confirmed active only 5 years earlier, could not be treated as an afterthought once that day came. The plan the team eventually built for that final act became known as the grand finale, and it was not a slow fade. Starting in the spring of 2017, Cassini flew 22 separate dives through the gap between Saturn's cloud tops and the innermost edge of its rings, a region no spacecraft had ever entered because nobody was entirely certain what was in it. That gap sits between a planet with hurricane-force winds and a ring system made of countless icebound particles, some no larger than grains of sand, others closer to the size of a house, all moving fast enough to seriously damage a spacecraft on contact. You can think of that corridor the way the engineers privately did, a road nobody had ever test-driven, taken at planetary speed. For the first of those dives, engineers were cautious enough that they turned Cassini's own large antenna into an improvised shield and flew that pass without transmitting home, listening for danger instead of reporting science. Controllers on Earth had no way to know in real time whether Cassini had survived it. The spacecraft stayed silent by design, antenna forward, and mission control simply had to wait out the entire pass and the return trip of a signal across the solar system. Before anyone knew whether there would be a second dive at all, nothing hit it. For the remaining 21 dives, they pointed the antenna back at Earth and gathered science in real time instead. Each pass brought Cassini closer to Saturn's interior than any measurement had ever come, close enough to finally weigh the rings precisely enough to estimate their age. which turned out to be a genuine surprise. Rather than dating back to Saturn's formation 4.5 billion years ago, the rings most likely came together sometime in the last 100 million years, which puts their birth somewhere around the age of dinosaurs on Earth, rather than the age of the solar system. Each pass also brought Cassini close enough to map the planet's magnetic field in detail nobody had managed before. That field turned out to be its own puzzle. It lined up with Saturn's spin axis almost perfectly, far more precisely than physics said it should, which made the length of a single Saturn day surprisingly hard to pin down even after 13 years of study. The same dives caught material raining directly out of the rings into Saturn's upper atmosphere, water and organic compounds falling out of that bright band overhead the way rain falls out of a cloud, at a rate fast enough that the rings are, on some timescale, far shorter than the age of the solar system itself, slowly emptying themselves into the planet they surround. Years later, a careful reanalysis of that same gravity data revealed that Saturn does not even have the small, sharply defined core older models assumed. Instead, its interior fades gradually from gas into a mix of rock and ice, diffuse rather than solid, reaching out to roughly 60% of the way toward the visible surface, a picture of the planet's inside that would have been impossible to draw without the extremely close, extremely risky vantage point those 22 dives provided. By that point, Cassini had already circled Saturn 294 times and traveled roughly 7.9 billion kilometers since leaving Cape Canaveral, nearly 200,000 trips around the Earth if you laid that distance out in circles instead of a straight line outward. It had been flying longer than some of the engineers now operating it had been alive. By the time its propellant finally ran low, it had reshaped nearly every part of the old textbook description of the Saturn system. Moons once assumed geologically dead, now confirmed active. Rings once assumed ancient, now suspected to be surprisingly young. Storms once glimpsed for a night or two through Earth telescopes now watched start to finish. It had one orbit left. For the final months, the flight team rehearsed that last day over and over in simulation, working through every way the descent could go wrong and what backup commands might still squeeze one more useful second of data home if it did. Nothing about the ending was left to chance, which is exactly the kind of ending engineers who have spent a career on the same machine want to give it. On September the 15th, 2017, Cassini committed to its final pass. It aimed itself down into Saturn's upper atmosphere while continuing to transmit its data live, not recorded for later, live, the way it had never been asked to operate before. As the atmosphere thickened around it, gas began pushing the spacecraft off its intended orientation, and its small thrusters fired again and again to correct, working harder with every second to keep the antenna locked on Earth. For close to a minute, they won. Then they could not fire fast enough anymore, and the signal stopped. Here's the part that is easy to miss. A radio signal takes well over an hour to cross the distance between Saturn and Earth, roughly the length of a feature film, which means that by the time the control room in Pasadena watched that line finally go flat, Cassini itself had already been gone for the length of a movie. It ended alone, on schedule, exactly where its own team had aimed it, and the news of it simply took that long to arrive. If you want a sense of the trust involved, remember that no human being had been anywhere near this spacecraft since the day it launched 2 decades earlier, and the plan for its death was carried out entirely by radio, from 900 million miles away. In the room, Program Manager Earl Mays called the moment out loud for the people around him. Spacecraft Operations Manager Julie Webster and the rest of the team at NASA's Jet Propulsion Laboratory had spent the morning watching numbers they had rehearsed against for years. When the signal finally went, people did not celebrate. Several of them embraced instead. Cassini's project scientist, Linda Spilker, said afterward that things would never be quite the same for the people on that team now that the spacecraft they had flown for 2 decades was no longer flying. Some of them had worked on Cassini since before it launched. Their careers had been built around a machine that no longer existed. It is worth saying plainly, call this what it actually was. Responsibility followed all the way through to an uncomfortable, correct conclusion, even against a team's own attachment to the machine that made its biggest discovery possible. Cassini was not lost, the way headlines sometimes flatten any spacecraft's end into a tragedy by default. It was retired, deliberately, by the people who understood exactly what it had found and what that finding demanded of them. Somewhere above Saturn's clouds right now, there is no wreckage and no debris field, nothing left in orbit to eventually go wrong years from now with nobody watching. Cassini became part of the planet it had spent 13 years studying, which is a stranger and more permanent kind of ending than most spacecraft ever get. For anyone who remembers watching Saturn's rings for the first time as a fuzzy smudge through a backyard telescope, or who watched an earlier rocket lift off decades before this one, that ending offers something rare in this field, a mission that got to choose its own final act, instead of simply running out of luck. The same question Cassini forced its own team to answer honestly, whether an agency is willing to protect a place it has not even proven is habitable, is going to come up again. NASA's Europa Clipper, launched in October of 2024 toward another of Jupiter's ocean moons, is already built around that same question. And whatever spacecraft eventually finishes studying Europa closely will face the same decision Cassini's team already made once, carefully, in public, for reasons that held up. That is Cassini's quieter legacy, separate from any single photograph or headline. It gave the people who fly the next generation of missions an actual precedent to point to, a working example of an agency choosing caution over convenience when a discovery raised the stakes of getting the ending wrong. If stories like this one are what you come here for, real missions explained honestly, without the exaggeration, consider subscribing. There's already serious talk in the planetary science community, more than 8 years after Cassini's own final dive, of a future mission built specifically to visit Enceladus again, a proposed orbiter and lander called the Enceladus Orbilander, carrying instruments sensitive enough to search directly for the kind of complex chemistry or something more that Cassini could only hint at from a distance. Whether that mission ever gets funded and built the way it is currently planned is its own long story, one worth telling properly another time. Thanks for watching, and thanks for caring enough about a machine like this one to sit through its ending.